So today we're gonna discuss a new topic, soil conservation. So the flow of our discussion will be, first we'll have discuss agriculture and its impacts to the environment. Second, we will have soil quality. And third, we will have soil conservation methods. So before anything else, before we start our discussion on soil conservation, let's have a little refresher or background with geology. All right, so geology is the study of the earth. So we start off with the earth's interior. So the earth consists of four layers. We have the crust, which is the outer layer. Next, we have the mantle. Then we have the outer core or the liquid iron outer core. Then we have a solid iron inner core. So let's take a look what consists of these layers.
The surface of the earth is covered by rocks and water bodies. But what about the inside of the earth? If we were to take a look at the earth's interior, we would see that the earth consists of four layers. They are the crust, the mantle, the outer core, and the inner core. The crust is the outermost layer of the earth. It consists of various landforms like mountains, plateaus, volcanoes, etc. The crust also consists of numerous rock plates. The shifting of these plates resulted in the formation of continents. In reality, the crust of the earth is a very thin layer. It is only 50 kilometers deep. The crust floats on top of the outer layers of the earth. The oceanic crust is thinner than the continental crust. The mantle forms the main mass of the earth. It is the layer just under the crust. It extends from Moho's discontinuity to a depth of about 2,900 kilometers. The mantle is a partly molten layer and can have temperatures reaching to 4,000 degrees Celsius. The upper layer of the mantle is called the asthenosphere. The hot magma from the asthenosphere travels to the surface of the earth and escapes as lava from volcanoes. In addition to the asthenosphere, there is a layer known as lithosphere. The crust and the uppermost layer of the mantle together form the lithosphere. While the asthenosphere has a depth of 400 kilometers, the lithosphere extends from 10 to 200 kilometers. The next layer of the earth is the outer core. This layer is exceedingly hot. It has a temperature of about 5,000 degrees Celsius. The outer core consists mainly of liquid iron. It has a depth of 2,200 kilometers. The core mantle boundary is located at 2,900 kilometers below the surface of the earth. We now come to the innermost layer of the earth, the inner core. The inner core has a temperature of around 6,000 degrees Celsius. This is nearly the temperature of the sun's surface. The inner core has a depth of 1,250 kilometers. Unlike the outer core, the inner core is in solid state. The intense pressure of the layers of the Earth ensures that the inner core remains solid in nature. Deep within the core of the Earth, there are radioactive elements such as uranium. These elements give off heat when they decay. This slows down the rate at which the Earth is cooling. But the core also has a very important function. It is responsible for the magnetic field of the Earth. The magnetic field is generated in the inner core, and the convections within the outer core result in the creation of magnetic fields. This magnetic field is what protects us from solar winds and high energy particles of the sun. The four layers of the Earth all have special functions. Now you know what the Earth looks like on both the inside and the outside.
All right, so that was the inside and outside of the Earth's um, the Earth. All right, so these are some of the physical properties of the Earth. So we have the mean radius in kilometers. We have 6,371 kilometers. We have the surface area, the oceanic surface area, the volume, the mass, which is 5.97 times 10 to the power of 24 kilograms. That's a lot. So we also have the density, the core radius, and we also have the mass of each layer. We have the atmosphere, hydrosphere, we have the mantle, bulk silicate earth, and we have also the core. So these are some of the physical properties of the earth. So as mentioned in the video, so we have three major parts or systems. We have the geodynamo system, we have the plate tectonic system, and we have the climate system. So in the geodynamo system, so we have already discussed this, that the inner core and the outer core is in charge of the magnetic field of the Earth. All right. Then next we have the lithosphere, the asthenosphere, and the deep mantle. So these consist of the plate tectonic system. Then at the climate system, so we have the atmosphere and the hydrosphere. So this is also called this is also where the biosphere is. All right. All right, so before we proceed, let's have a little refresher on our statics subject. So, stress is the force exerted per unit area, and the strain is the physical change that results in response to that force. So, when applied stress is greater than the internal strength of, let's say, a rock, strain results in the form of deformation of the rock caused by stress. So strain in rocks can be represented as a change in rock volume and or rock shape, as well as fracturing the rock. So there are three types of stress. We have the tensional, compressional, and shear. So we have already, if you have taken up statics, so we have you have discussed this in your subject. So tensional stress, as you can see right here, tensional stress involves forces pulling in opposite directions, so which results in a strain that stretches and thins the rock. So there is breakage at the center, or where there is breakage when there is tensional stress. Now, if we have compressional stress right here, it involves forces pushing together. And compressional strain shows up as rock folding and thickening. All right, so there's a folding of rocks here. That's compressional stress. Now we also have the shear stress. So involves transverse forces. So the strain shows up as opposing blocks or regions of material moving past each other. So that is shear stress. Okay, so what does this have to do with our discussion? So all of these stresses or strains happen also in the Earth's crust. So as you can see here at this picture at the bottom, so you can see there are ridges or it's not uniformed, right? So this is due to stress and strain. So as you can see here in the illustration at the top, so for example, there is stress. So there is a fault here, right here. Fault. This is the fault, right? And there you will, if there's strain, there's already strain due to the stress. You will see the fault scrap, and there is a hanging wall. So same here, right? Right here. So this side drops down relative to the other. So this is also what you call the footwall. And this is the hanging wall. So this is what moves. All right. So like the stress and strain, so it is what is applied to earthquakes and fault lines and trenches. So in the Philippines, we have we actually have lots of fault lines and stretches surrounding and inside our um, archipelago. So as you can see here, um, the oceanic trench, we have oceanic trenches at both of the sides. So we have the Manila Trench on this side, the Negros Trench, the Sulu Trench, the Cotabato Trench, and also on this side we have a very long trench, which is the Philippine Trench, and we also have the East Luzon here, right here. All right. We also have a fault line. So at the center, we have a fault line here. That is a fault line. We also have very many active volcanoes and quaternary volcanoes. So that also causes earthquakes. Okay, so what is actually earthquake? So earthquake energy is actually seismic energy. All right. And it travels through the earth in the form of seismic waves. So to understand some of the basics of earthquakes and how they are measured, consider some of the basic properties of a wave. So as you can see here, this is there are one, two, three waves here. So waves describe a motion that repeats itself in a medium, or let's say a rock or unsol unsolidate unconsolidated sediments in our case. So the magnitude or the height of the motion is the amplitude of the wave. So as you can see here, this is the amplitude. The number of repetitions of the motion over time or cycles per time is called the frequency. And the inverse of frequency, which is the amount of time for a wave to travel one wavelength, is the period. So when multiple waves combine, they can interfere with each other. So when the waves are in sync with each other, they will have a constructive interference. All right, so as you can see here in the blue and the green wave, so they are in sync with each other. When the influence of one wave will add and magnify the other, so that is constructive interference. If the waves are out of sync with each other, they will have destructive interference. So if two waves have the same amplitude and frequency and they are one half wavelength out of sync, the destructive interference between them can eliminate each wave. So this process of constructive and destructive interference is illustrated here. All right. So the release of seismic energy is actually explained by the elastic rebound theory. So the elastic rebound theory is the gradual accumulation and release of stress and strain. So when rock is strained to the point that it undergoes brittle deformation, built up elastic energy is released during displacement, which in turn radiates away as seismic waves. All right? So when elastic energy is released during displacement, which in turn radiates away, so it will form seismic waves. When the brittle deformation occurs, it creates an offset between the fault blocks at a starting point called the focus. This offset propagates along the surface of rupture, which is known as the fault plane. So the fault blocks of persistent faults like uh, a fault line in Utah, they are locked together by friction. So over thousands, hundreds and thousands of years, stress builds up along the fault. Eventually, stress along the fault overcomes the frictional resistance and slips initiates as the rocks break. So the deformed rocks snap back. So mura siya og ni rag na stuck kay siya, then it finally na release siya. So the deformed rocks snap back toward their original position in a process called elastic rebound. So bending of the rocks near the fault may reflect this buildup of stress, and in earthquake-prone areas like the Philippines. So strain gauges that measure this bending are set up in an attempt to understand more about predicting an earthquake. So in some locations where the fault is not locked, so seismic stress causes continuous movement along the fault called a fault creep. So this is where displacement occurs gradually. So hinay-hinay lang siya. Dili siya wala siya rebound or dili mo snap back. So after seismic energy release, energy begins to build up again during a period of inactivity along the fault. So the accumulated elastic strain may produce small earthquakes or near the main fault. These are called foreshocks and can occur hours or days before a large earthquake, or they may not occur at all. So the main release of energy occurs during the major earthquake is called the main shock. Now, after shocks may then occur to adjust strain that built up from the movement of the fault. They generally decrease over time. So I have already mentioned to you seismic waves. So these are an expression of the energy released after an earthquake. So seismic waves occur as body waves and surface waves. When seismic energy is released, the first waves to propagate out are body waves that pass through the body of the planet. Body waves include the primary waves, this is the primary waves or P waves, and secondary waves or S waves. So primary waves or P waves, these waves are the fastest traveling wave through rock. So it's felt first after an earthquake. So these P waves is a type of body wave that pushes and pulls rock and liquid in the same direction as the wave moves. All right, so this is an illustration of the P waves. All right, so it moves through rock and liquid. All right, so after the P waves, there are secondary waves or S waves. So this is the second fastest moving. It travels through solids only. So solid lang siya, no liquid ha. S waves only travel through solids. So body wave, it is a body wave that shifts rock side to side at a right angle. So this is an illustration of the S wave. All right. Now, after the S wave, we have surface waves. All right. So this group of waves is slower than P waves and S waves and act much closer to the surface of the earth, hence the name surface waves. All right. So these are primarily the waves, kinds of waves. All right. Now, there are two types of surface waves. We have the Rayleigh waves and the love waves. So these differ in what directions they shift the Earth's surface. So in a love wave, so it moves the surface side to side at a right angle to the direction of the wave, while the Rayleigh wave moves the surface in a rolling circular motion the same way an ocean waves move. So it's forward, down, and back up. Forward, down, and back up. So these are the two types of surface waves. So this is an illustration of the primary, secondary, love wave, and Rayleigh wave. So as you can see here, this is a seismogram of an earthquake. So you can see here the P wave, which is the fastest traveling wave. Then we get the surface wave, and then, I mean the S wave or secondary wave. Then we get the surface wave. So as you can see, it's much, the waves are quite bigger because it is closer to the surface. So how do we get these seismogram? So we actually measure um, through a seismograph. So it is used to record the motion of the ground during an earthquake. So the only difference between the horizontal seismograph, which is this is the horizontal, and the vertical seismogram is that it is direct, in the horizontal seismogram, it is directly attached to the ground, while the vertical seismogram, or seismograph rather, makes use of a mass. All right. So this is an illustration on how the seismograph works. So remember that S waves are shear waves and P waves are compression waves or shear stress. S waves are shear stress and P waves are compressive stress. Now we also know that earthquakes can happen underwater, which in return can cause dangerous tsunamis rather. So just like this. So there is a fault or a trench, and when the seismic energy is released, it causes a tsunami. So now, why is a tsunami dangerous as it approaches shallow water? So in the illustration here, as the depth of the ocean becomes shallower, the waves slow down. As you can see here, the waves slow down and pile up on top of itself, making large, high amplitude waves. So as you can see here, they're getting closer to each other as the shallower the depth of the ocean is. All right. So here is a simulation of a, what you call this, a tsunami. All right. So what is the difference between tsunami and a tidal wave? So if we might it might look like it's the same, right? But a tidal wave, although both are sea waves, a tsunami and a tidal wave is different. And they are both unrelated. So a tidal wave is a shallow water wave caused by gravitational interactions between the sun, moon, and earth. All right. A tsunami, on the other hand, is an ocean wave triggered by large earthquakes that occur near or under the ocean. So those include also volcanic eruptions, submarine landslides, or by onshore landslides in which large volumes of debris fall into the water. So you might also remember the very big tsunami in Japan, or that was caused by the Japan Trench. So this is another simulation of the tsunami scenario in the Pacific Northwest. Now, how do tsunamis form? So let us look at this video. So just like this, there is an earthquake or a breaking of a formation of a trench. So that causes a tsunami. So the waves actually travel from the center of the trench to outside, outward. And so as the water, as the depth also decreases, the waves also intensifies since, like I said earlier, um, as the depth becomes shallower, it also becomes the waves also meet each other, and they pile up to form a high magnitude wave, right? So as you can see on the video, so this is what happens during a tsunami. Now, earthquakes are not only caused by trenches and fault lines. It is also caused by volcanic eruptions. So, a little background: phreatic eruptions are steam-driven explosions that occur when water beneath the ground. So, as you can see here in the illustration, beneath the ground or on the surface is heated by magma, lava, hot rocks, or new volcanic deposits. The intense heat of such material, so it can go as high as 1170 degrees Celsius for basaltic lava. This causes water to boil and flash steam, thereby generating an explosion of steam, water, ash, blocks, and bombs. All right. Now, with all that said, the Philippines is highly susceptible to very many kinds of natural disasters. So, as you can see here, this is a phreatic eruption of the Taal volcano last January 2020. So there are also earthquakes. All right. So as you can see here, this is a bridge that broke in Surigao during February of 2017. So the Philippines is located along the Pacific Ring of Fire and on top of two tectonic plates, which is the Eurasian and Pacific plates, volcanic and earthquake generators, and there are also very many active faults and trenches. So this is the Pacific Ring of Fire. So as you can see here, here is the Philippines. Okay, so we are part of the Pacific Ring of Fire, along with other neighboring countries. This is also a earthquake during September of 2013 in Bohol. Also, Philippines does not only experience earthquakes and what you call this volcanic eruptions, we also experience droughts or El Nino. So this is a picture of Davao del Sur in 2016. So we had a very bad El Nino at that time. So El Nino is caused by the trade winds. So the trade winds blow towards the west. That is what normally happens. Now, during an El Nino, anomalous bursts of winds blow toward the east or westerlies. All right. So that makes above average sea surface temperatures in the western and central Pacific Ocean. So as you can see here, the Philippines is here. Now this is in neutral conditions, but in El Nino conditions, since there is a very, what you call this, there is a high surface temperature, so the winds that has high temperatures blow towards the Philippines, making it um, very hot. So init siya, init ang high ang temperature sa surface sa wind. So that causes the El Nino. Now in the Philippines, we also experience a lot of what you call this, a lot of typhoons, heavy rainfall. So aside from the opposite of El Nino, we also have very wet and rainy days. So in the Philippines, it is very important to measure rainfall. So this is what you call a rainfall gauge. So uh, it is used by meteorologists and hydrologists to gather and measure amount of liquid precipitation over a predefined area over a period of time. So this is an example of a two types of rainfall gauge. So we have this one. This is very automatic, so it measures automatically with this. While this one, it's very manual, so you measure it on your own. All right. So you can actually have this in your at home. It's very inexpensive. So there are many sites, or you can visit many sites that would give you data on how much rainfall there is, so or precipitation data. So with that said, the Philippines um, is very highly susceptible to typhoons due to its location in the Pacific typhoon belt. So for example, this is Typhoon Yolanda. So this has been the most devastating typhoon to date. All right. So this is the monthly average of occurrence of tropical cycles or cyclones in the Philippine area of responsibility or PAR. So actually during August and July, we have um, the most number of tropical cyclones. So these are during our wet season. So as you can see here, the Philippines have very many tropical cyclones to date. So this is cyclone tracks, an example of cyclone tracks from 1948 to 2005. So we had a total of 1,128 tropical cyclones during that period. So as you can see here, So on the lower region, we don't really have that much, right? But now, these days, probably due to climate change, so tropical cyclones get a much, much lower, and the Mindanao is now being affected. So that would be it for our introduction